Quantum computers. Quantum computers are an exciting and rapidly developing technology that leverages the principle of quantum mechanics. Key conception: qubits. Qubits, short for quantum bits, are the fundamental units of information in quantum computing, analogous to the bit in classical computers. However, unlike classical bits, which can only exist in one of the two states, 0 or 1, qubits can exist in multiple states simultaneously, thanks to the principle of quantum mechanics. Let's look at the key concepts and properties of qubits to understand how they work and why they are so important in quantum computers. A qubit is a basic unit of quantum information and is typically represented as two-level quantum system. These two states are often referred to as basis states or computational states, usually denoted as 0 and 1. However, due to quantum mechanics, a qubit can be in superposition of both states at once, meaning it can be partially in 0 and partially in 1 simultaneously. This superposition allows quantum computers to perform many calculations simultaneously, which is what gives the potential to solve certain problems exponentially faster than classical computers. Entanglement is a unique phenomenon where the state of two or more qubits become linked, such that the state of one qubit cannot be described independently of the state of the other. If you measure one qubit, the result will instantaneously be the state of the other entangled qubit. Entanglement is a key to many quantum algorithms, as it enables quantum parallelism and allows quantum computers to perform operations on multiple qubits at once in a correlated way. For example, if qubit is measured to be 0, the other will also be 0, and similarly, if one is measured as 1, the other will be 1. Quantum interference occurs when the probability amplitude for different possible states of qubit combine in such a way that the possibilities are enhanced, and others are cancelled out. This is similar to wave interference in classical physics. Constructive interference occurs when the amplitude reinforce each other, and destructive interference occurs when they cancel each other out. Quantum algorithms rely on interference to amplify the correct solutions to a problem, and diminish the incorrect ones, making quantum computation more efficient. Types of qubits and implementation. Various physical systems can be used to create qubits, each with its own strengths and challenges. Some of the most common qubit implementations include superconducting qubit. These qubits are built to use superconducting circuits, which can carry current without resistance. They are manipulated by microwave pulses and are one of the leading approaches in quantum computing research. Trapped ion qubits. Ions, otherwise charged atoms, are trapped using electromagnetic fields, and their quantum states are controlled with leaders. These qubits are known for their long coherence time and high precision. Another interesting type of qubit is photonic qubit. Photons, particles of light, can be used to encode qubits, where quantum states are presented by the properties such as polarization or phase. Photonic qubits can be manipulated and transmitted easily, making them ideal for quantum communication. Another interesting type of qubit is topological qubit, a more theoretical approach. These qubits would rely on particles that exist in two dimensions, and their unique braiding properties to store and manipulate quantum information. Topological qubits are less susceptible to error due to their robustness against local disturbances. Quantum gates. Quantum gates can manipulate qubits in a similar way that classical logic gates manipulate bits. However, unlike classical gates, which are deterministic, quantum gates can change the state of qubit in a reversible and probabilistic way. Common quantum gates include Pauli X gate, also known as NOT gate. It flips a qubit from 0 or 1 or vice versa. Hadamard gate. It creates a superposition by transforming a qubit into an equal mix of 0 and 1. CNOT gate, also known as controlled NOT. A two-qubit gate that flips the second qubit if the first qubit is in state 1. Phase gates modify the phase of a qubit state, altering its probability amplitude. Quantum algorithms. Quantum computers use qubits to run quantum algorithms, which can outperform classical algorithms for certain tasks. Notable quantum algorithms include short algorithms and Grover's algorithms. Short algorithm: a quantum algorithm that can factor large numbers exponentially faster than classical algorithms. This has significant implementation for cryptography. Grover's algorithm: a quantum search algorithm that can search unsorted database faster than classical algorithms, providing a quadratic speedup. There are some challenges with qubits. One of the examples is decoherence. Qubits are very sensitive to their environment. External noise and interaction with the environment can cause qubits to lose their quantum properties, other words decohere, which leads to errors in quantum computations. Researchers are working on quantum error correction and improving qubit stability. Scalability: building a large-scale quantum computer requires managing a large number of qubits, which is difficult due to the sensitivity and the complexity of maintaining coherent superposition over time. Many qubit systems still struggle with scalability. Quantum error correction: since qubits are prone to errors due to decoherence and noise, developing reliable quantum error correction techniques is essential. This involves encoding quantum information across multiple qubits in a way that detect and correct error without disturbing the quantum state too much. Thank you for listening to this podcast on quantum computers. Until next time, curiosity adventures through the fields of science.